Hi everyone, I'm Jiayuan, and today I'm presenting our recent work on improving the differential privacy analysis of the noisy stochastic gradient descent algorithm. This is joint work with my advisor Reza Shokri from National University of Singapore. So as a bit of background, privacy risk exists everywhere in modern machine learning algorithms, and by privacy risk, we mean that the output model of the training algorithm may leak sensitive information about individual users of its in its training data set. So for example, by purely observing the model prediction and model parameters, the adversary can infer whether a particular user data point is in the training data or not. And in some extreme scenarios, they can even partially or completely reconstruct a training data record. So these privacy risks all threaten the application of machine learning in some privacy sensitive applications, and therefore it calls for training private machine learning models. So to protect user privacy, we can train a machine learning model under differential privacy guarantee. Differential privacy is a quantitative notion that bounds the worst case information leakage of a randomized algorithm. Loosely speaking, it ensures that the distribution of the algorithm's output on any neighboring input datasets are indistinguishable. This means given an observed model, which is a sample from the distribution of output, the adversary cannot infer whether the model is trained on dataset D or any of its neighboring dataset D prime. There are multiple ways to quantify this indistinguishability, and it gives many variants of differential privacy definition. And in this paper, more specifically, we focus on the Rainy differential privacy notion, which quantifies this indistinguishability with the Rainy divergence. So we use this mainly because it's convenient for our analysis technique, and also it can be easily converted to the standard epsilon delta differential privacy. And the algorithm that we are focusing on is the noisy stochastic gradient descent algorithm. And at a high level, it consists of multiple iterations, and in each iteration, a minibatch is sampled and the model is updated based on the sensitive data from this minibatch. This update alone is deterministic and therefore does not offer any guarantee of indistinguishability, and thus does not satisfy differential privacy. So to make it differentially private, we need to add carefully calibrated noise to this sensitive update. So the question is, this noise, although it reduces privacy cost, it tends to degrade empirical accuracy of the final trained model also. As a result, we often see this kind of trade-off in differentially private learning, where at smaller privacy cost, the accuracy of trained model also tend to be worse. So because the actual privacy loss of an algorithm is often difficult to analyze due to various reasons, therefore people often can only obtain upper bounds for this privacy cost and plot the curve with the upper bound. Privacy cost upper bound crucially affects the privacy accuracy trade-off of a fixed training algorithm. And if we can obtain tighter privacy upper bound, we can expect to obtain much better privacy accuracy trade-off. That is, have a more accurate model at a fixed privacy cost. And the central problem that we want to study in this paper is that how could we prove tighter upper bound for the noisy stochastic gradient descent algorithm so as to enable better privacy accuracy trade-off? There are, of course, various privacy analysis methods for the noisy stochastic gradient descent algorithm. And most of them share a similar feature, that is they break the algorithm into subroutines and use composition analysis to obtain the privacy bound for the algorithm. And this is because the distribution of the final output is usually very complicated after many iterations of update, and thus directly analyzing the last iterate is often difficult. And composition, therefore, studies a slightly different problem where the adversary is not only able to observe the final model, but also all the intermediate models after each iteration. So we can then bound the privacy cost for each update and then sum them together to bound the total privacy cost. And then by definition, this privacy cost for releasing all the intermediate models is an upper bound for the privacy cost of releasing the final model. However, this gap between adversary model also makes this privacy cost obtained by composition analysis to grow linearly with the number of iterations k, and therefore it is not quantitatively that ideal when you want to train a large number of iterations. So how can we maybe obtain a better privacy bound in the large epoch regime? So because this gap is caused by the adversary assumption, naturally we want to improve this bound by assuming that all the intermediate models are hidden. So what is different in this analysis is that now, instead of looking at one fixed minibatch in one update, we need to look at a sequence of minibatch because we are assuming the algorithm states to be hidden. And observe that because the update is not done on the entire data set, only some minibatches may contain a differing data record at the same time. So we can observe that this update that involves the differing data set will induce privacy cost. However, all the other minibatches that only access shared data points between neighboring data sets serve as randomized post-processing that does not increase and even decreases the privacy cost. And therefore, the central, the main problem that our paper deals with is try to prove this hidden state privacy bound for noisy stochastic gradient descent algorithm that quantifies this privacy amplification due to the stochastic sequence of mini batches. That is, one differing record may not occur in every mini batch, and the randomized post-processing may serve as additional amplification to the privacy cost. And we first look at the first source of amplification, that is the additive noise added in the update that does not access the differing data record decreases the privacy cost. So how do we quantify this amplification? So we first fix this mini batch sequence because now we are studying the effect of randomized post-processing specifically. And the difficulty for this is to model the change of distribution during the randomized post-processing update. And moreover, we need to translate this change of distribution to the dynamics of privacy loss before and after this update. So our result for this privacy bound before and after randomized post-processing is that suppose that the training has gone for k epochs and j iterations, and the intermediate models until now is theta kj. Then after one update on a mini batch bkj, we want to quantify how much the privacy loss between the models after the update changes compared to the privacy cost for the models before this update. So our result says that if the distribution of the parameters before the update satisfies log Sobolev inequality with a constant C, and if the minibatch gradient descent mapping is L-Lipschitz, then we can obtain a recursive privacy bound that says if the differing data record is not in the minibatch used in this update, then the privacy loss decreases multiplicatively. And if the differing data record is in the accessed minibatch, then the privacy loss increases additively. So the constant, here are some constants that appear in this theorem, and the main advantage of this theorem is that it is recursive, so it's easy to extend it to multiple epochs and multiple iterations. And by using this recursion, we can prove a converging privacy bound for strongly convex and smooth loss functions. So in this plot, the solid line is our hidden state privacy bound. And if we compare it with the previous composition-based analysis, we can see that it converges while the composition-based bound grows linearly with K. And we also compare this bound with previous work that quantifies a similar dynamic bound for noisy gradient descent. And because there is no amplification due to stochastic minibatches, we observe that our bound is significantly smaller than the bound for the naive extension of the gradient descent bound to stochastic minibatch setting. So now that we have obtained a privacy bound for a fixed minibatch sequence, we then look at the second source of amplification, which comes from the minibatch sampling process. That is, there is certain probability that the differing data point is in the first minibatch, the second minibatch, so on and so forth. And then if we want to quantify the privacy cost, the key difficulty is that this distribution of final output is now a mixture of a large number of components, where each component is the conditional distribution of the output given one minibatch sequence. And this number of components is large, especially when the minibatches are repeatedly resampled during each epoch, so that there will be combinatorically many number of possible minibatch sequences. And to deal with this difficulty, we apply the joint convexity result of the scaled exponentiation of Rayleigh divergence and use it to layer by layer decompose the mixture distribution and recursively bound the privacy loss between the mixture distributions. So this, by further accounting for this amplification, we can prove that the privacy cost between the mixture distribution under shuffle and partition scheme for sampling the mini batches are smaller than the privacy loss between its worst case components, which in our case is when the differing data record is in the last mini batch of each epoch. And when we compare it with the composition-based bound, again, we can observe that now it's smaller than a composition bound after a smaller number of epochs. So now that we have obtained a privacy bound that is tighter than composition in the large epoch regime, we can now return to our central problem, which is, does this privacy bound enables better privacy accuracy trade-off for learning tasks? So we train regularized logistic regression model on scatternet features for classification on CIFAR-10, and we observed that compared to previous work that uses composition bound, the optimal accuracy on the DP budget epsilon equals 3, delta equals 10 to the minus 5 is significantly larger, and it is also more closer to the accuracy under no noise, that is the accuracy that for training non-differentially private models. And this gain is because if we observe the training process, it's because the training process converges very slowly and the optimal test accuracy is not reached even after 1,000 epochs. And this gives our privacy bound a gain because it is converging at larger number of epochs, while composition-based bound only allows for training a limited number of epochs under a differential privacy budget. Meanwhile, we also did experiments for alternative setting where the learning task converges rather quickly. It is the transfer learning scenario where we fine-tune the last layer of a pre-trained model on CIFAR-10. So the pre-trained model is trained on a different data set. And we observed that this the accuracy for this learning task converges rather quickly within few epochs. And as a result, our hidden state privacy bound in this case only enables slightly better accuracy than composition. And this is because here composition is only applied to a few number of epochs. So to conclude, we observed that our hidden state differential privacy bound enables training differentially private models with better accuracy when the training process converges slowly. And meanwhile, composition-based privacy bound is empirically not so costly for training process that converges within few epochs. And this is an interesting direction, and we observe that there are still a lot of open problems to solve, such as the hidden state privacy bound under more relaxed conditions without strong convexity and smoothness, and or like tighter bound for the hidden state privacy amplification due to stochastic sequences of minibatches. And that's the end of my presentation. Thank you for listening.